between the particles act like a spring. They will try to keep the distance as a fixed distance. They will pull the particle if they try to leave, and they will push them if they try to get close. So if I try to pull this table apart, these spring-like forces will bind the particles together, so I cannot just tear off a particle from this table. But if I try to squeeze it, it will try to bounce back and refuse to change its shape. So I know there must be some other forces besides gravity. So you can have a solid on Earth or on the universe, in the universe. Okay? So there are forces other than gravity. That's the takeaway point. This is the force binding particles in an object together. There should also be forces that stop one object to get into another object. You see all this thing on the table is not sinking into the table. So you know between the table and whatever thing is on top of it, there must be some force between the table particles. Let's say these are the particles of the block. They are bind with each other, so they can have a fixed shape and volume. And the particle in the table should also have some forces binding them together. Between the particle of the block and the table, the spring is like pushing, but they are not connected. So we know they should not be connected because if I try to move this thing away from the table, it's not sticky. I can easily pull a weight away from the table, but I cannot push it into it. So it's like a disconnected spring. They will refuse to get close, but if you want to leave, they won't pull you because they are not connected. But there's no spring. This spring aren't real. The world is just made with particles. These springs are just some cartoon helping you to describe what the property of these interactions are. There are interactions keeping particles together, and there are interactions refusing them to get close to each other. Okay? Good, so now we are done with particles. It's time to get real into microscopic objects. We don't want to just study the orbit of Venus. We want to apply physics in our real life. And in our real life, nothing is particle. They are all microscopic objects. So we need to know how to deal with it. Let's say we are looking at a ramp and a block is sliding down. When we look at it, we are looking at a bunch of particles. The block is some particles. And the ramp is also some particles. So if I want to describe the motion of this block sliding down, I can describe the motion of all these particles. That's one way. But it is obviously unnecessary. When we look at a block sliding down, we don't really care about the detail of what's happening to all these particles. We want to know this block as a whole and how this block is moving as an entire system. So we need to know how to deal with a system, which is, again, a bunch of particles. No matter what we're looking at, it will end up being a bunch of particles. a system is just we choose some of its particles and we call it a system. There's no rules about what particles you should choose. I'm going to choose these 3 particles to be my system, and this is my system. But there are some obvious choice. For example, if I want to analyze the motion of this block, the obvious choice is to choose all the particles inside this block as my system. But what I'm going to do next has no restriction on which particle you choose. A system is just a bunch of particles. Okay? And it works for any case because no matter what you're looking at is a bunch of particles, and this is, and you can always choose any of them and say that's your system. Now, if I look at one of the particles here, I choose this 3 to be my system. So one has mass m1, another one has mass m2, and there might be more particles inside my system. So let's say there are n particles in my system. What I'm going to do is to look at F equals ma on one of the particles. When I look at this particle, particle 2 is giving it a force. Let's call it F12. This is the force acting on particle 1 by particle 2. Similarly, the force acting on particle 2 by particle 1 is F21. That is my notation. Okay. There are other forces acting on M1. Mn can also act a force on it, so there's F1n, something like that. So the total force acting on the first particle will be the force acting on the first particle from the second particle, the force acting on the first particle from the third particle, and you keep adding them until you reach the force acting on the first particle from the nth particle. That's not yet the total force, because we only call this part, or we only call these particles to be our system. There are particles outside the system, and they can interact with the particle inside your system, because what you call the system is just something you choose. This dashed line is not physical. You can choose any particles to be your system. But when the thing outside the system is acting a force on a particle inside the system, we call that force an external force, because it is outside your system, and an external one is the external force acting on particle 1. All the particles outside the system can give you an external force. What I'm writing here is the sum of those forces. I'm just going to add all the force from outside the system, and together they act as a total force, Fex1, on the first particle. So after adding that into my forces, this is the total force acting on the first particle. And according to Newton's second law, it will equal to the mass of the first particle times the acceleration of the first particle. Okay? Let's do the same thing for the second particle. For the second particle, the thing outside the system can also exert forces on it, and we call the sum of them external force acting on the second particle. So there are some external forces acting on the second particle, and the first particle can give the second particle some forces, and we call that the force on second particle by first particle. We can have the force on second particle by third particle, we skip 2 because the second particle will not add force on itself. It only comes from other particles. So until the nth particle can also exert a force on the second particle. And the total force will be the mass of second particle times its acceleration. Okay? We can continue to do the same thing for all the particles until we reach the nth particle. We have n particle in our system, and this is the final one. It will get some external force. The other particles, like the first particle, can give the nth particle a force. The second particle can also give the nth particle a force until the n minus 1th particle. Make sense? And this will be the mass of the nth particle times its acceleration. Now, all these forces are called external force. And these are the interaction between the particles inside the same system. We call this internal force. What I'm going to do is to add all these equations together. This means that if I'm doing A plus B equals C, and 1 and D plus E equals F, and I add them together, I got A plus B plus D plus E on the left hand side, and C plus F in the right hand side. This is what I'm going to do. Okay? So, when we look at this, we think that, oh, we're screwed, there's so many terms. But there's a thing called Newton's third law. The force acting on the first particle by second particle should be equal and opposite of the Newton's third law pair, F21. F12 here and F21 satisfy the Newton's third law. They should be equal in magnitude but opposite in direction. So if I add them together, what will I get? Good, 0. So these two cancels. Okay? Similarly, if I look at F1n, there's a Fn1 over here, and they also cancels. Let's look at F13. Down here, there's going to be